super fast online clustering. Now, to start with, who am I? I'm the guy with the red hat, usually with the red hat, sometimes not, sometimes Apache oriented. At the end of the slides will be my contact information. What I do is I'm Chief Application Architect for MapR Technologies. Wow. That's the aegis, where I get paid for doing things like this. I'm also a committer on Mahout, champion for the brand new Apache Drill project, and PMC member for Zookeeper and early contributor to Hadoop, in that I answered more questions than anybody for a long time and bought the beer at the first hug. Did some other things too. But the question is why would we want to do clustering? One good reason, as far as I can tell from the mailing list, is that other people do it. So people think that it's very fashionable because a lot of people talk about it, therefore they want to do it. And honest to God, I swear some people do clustering because other people do clustering. That's not why I do it. Because cluster distances, if you've got a bunch of clusters there, the distances to all the different clusters. What's blinking?
The one by the button.
Okay.
Yeah.
It's the bullshit meter.
I'm going to get away from that meter. The distances to all of the different clusters is an interesting position measure in the distribution of points in your training data. And it often, if you have like curled up, strange, almost linearly shaped or low-dimensional manifold data, these cluster distances make very interesting features because the one that you're closest to tells you a lot about which general part of the low-dimensional distribution that you're in, and the other distances to nearby clusters resolve that ambiguity. And these very often allow you to have very, very interesting classifiers, linear classifiers based on cluster distances that give very interesting and complex nonlinear classification behavior for your actual data. So that's a better reason than the fashion-based one. And another one is that good clusters can help build really fast nearest neighbor search engines. And nearest neighbor search can do a lot of things. Like if you're going to do some dot product-based classifier on a whole lot of data, if you only do it on the stuff that has really high dot products, therefore has close proximity, you may get away with an approximate answer that's as good as if you've done it on everything, because you were going to throw away everything with small dot products. Anyway, so let's just do the interesting part. Or it may be nice because you want to build a model by just averaging nearby points. It's a very, very simple model. It's a very, very easy way to build a model, and that often can give you very high quality models at very, very low complexity in terms of the modeling process itself, because you've got the data set and you're just probing it, saying what are things like this like? And so you can have a very agile modeling process while you're experimenting with new features and things like that. So that's a very nice reason to use clustering. And because we can use the clustering of the data as a surrogate for data. So if we want to train on 1 billion data samples, one of the things we can do is we can reduce this data samples down to some surrogate representation which fits in memory. And then we might do some complex training algorithm on that in-memory representation. That's very cool. Or it lets us do visualization against really big data sets that would never work in our visualization system. So these last three are plausible reasons to do that. So I'm going to talk about nearest neighbor models a bit more. I'm going to talk about k-means algorithms and why the standard algorithm is not so good, and this class of what we call surrogate methods or streaming k-means algorithms and how they actually work. And I'll provide a few results, not a whole lot yet because it's new. And that's the way new things are. So nearest neighbor models, we want to find the k-nearest training examples, and we're going to use the average of the target variable from those nearest neighbors. That's it. That's how we're going to build models. And back in the day, the dark days, before they had dirt, when they only had rocks to eat, Alan Lapides used to come up and he worked at Los Alamos in the complex systems group, and there were two schools of thought. The neural network guys would come up with these amazing neural network learning algorithms, which we now call stochastic gradient descent. And back then, they required supercomputers, supercomputers like this one, to run. So there were training algorithms because people didn't really understand how simple that was. And then Alan Lapidus would come up and he would say, look, I can do this with a nearest neighbor model. And it's easier. And then the neural net guys would work for several months and they'd see we could match that. And he'd go, yeah, but look, I could do this. And they go, oh, and they grunt for several more months and they'd see we could match that. And so these nearest neighbor models were really, really frustrating for some people, but really, really liberating and exciting for others because they could build these very, very interesting behavior models just by looking for the nearest things. But, if you have 100 million points in your training data, you have to search against 100 million data points. That's a lot of data points and a lot of comparisons to do. So you may wind up with a stunning amount of math. Like, I hate numbers like 10 to the 20th when I'm talking about how many units of time this program is going to take. And it's also, if we're looking for something like fraud, it's got an incidence of less than 1%, and so we need to look through the top, say, 50,000 nearest neighbors to get a good average. That's a lot. That's not like a search engine that needs the top 100. So there's a lot of work there, and this work was in conjunction with one of our customers, a large bank, and they had a prototype. They did 3,000 queries against 200,000 things, and it took about 6 hours. And that's how long they wanted to do 20 million queries against 25 million things. So this is like 10,000 times too small there, and it's about 100 times too small there. So that this prototype was about 1 million times too slow. So they were sitting there going, well, this is not going to happen. The goal was to make that prototype or that technique viable for them. Happily, the implementation was in SAS, and so that's such a bizarre language that we got a factor of 100 or more right off the bat, just by switching to a real language. But we still had over 100, almost a factor of 10,000 that we had to make up, or 1,000, in order to get an acceptable thing. Here's a picture of how nearest neighbor works. We have 4 colors of dots that are kind of clumpy, but you see weird things like there's a yellow one way over in the red world and a purple one in the blue world, and so on. And so if we wanted to decide what color a new dot here would be, we could draw a little circle, and we could say, it's red, right? That's pretty simple. And if we wanted to decide what color should go here, it's going to be this odd cyan color. And if we want to decide here, it looks kind of debatable. It's kind of like 2/3 red and 1/3 yellow, but we can at least say it's probably not any of these 2 colors. That's the intuition behind these models. It's really, really simple. And it'd be nice to build these advanced predictive models on such a simple philosophical base. And other types of modeling, like logistic regression, depends on these linear separability, but this nearest neighbor just doesn't care. It just depends on whatever the data looks like. And having lots of data can give you really complicated separations. K-nearest neighbor works very well if logistic regression works. It usually works very well even if logistic regression fails because of a nonlinear decision surface. And things like CART or boosted trees and things like that to give nice properties. But K-nearest neighbor usually gives comparable results if the coordinates are scaled reasonably to these other advanced techniques. So it's a really powerful technique if we could just do it. So the speed we want is 20 million queries against 25 million references in about 10,000 seconds. So, and we'd like to be able to scale it up, of course, and we'd like to scale it linear and horizontally and all the fashionable terms. We probably need, and this is based on just empiricism, about 50% overlap with the correct search result. So we're willing to say that as long as we find a lot of close by points, it's okay if we don't find exactly the nearest ones. but find points that are about as near as the nearest ones and have a pretty good overlap with the actual nearest ones. And we can evaluate it by subsampling, so we can do many fewer queries, for instance, against the 25 million. And then we can do exhaustive search for those, get what the true answer is, and we can evaluate that. Now, we don't have here criterion according to accuracy, because what we want to do is work on this in abstract as opposed to on any given problem. And so what we'll do is we'll generate, when we get down to evaluating, we'll generate data at random and then just evaluate how well the nearest neighbor search is working. And we try to build lumpy data that replicates the experience of real data. So how hard is it? This is going to be about 50 petaflops. One CPU gets about 5 gigaflops. In Java, maybe 2. That's my laptop speed. That's not a real one. So we need about 10 million CPU seconds, or about 10,000 CPUs to do this. That's more than I want to buy, more than the customer wanted to buy. And real-world efficiency might make that 100,000 CPUs. So this is not good, as they say. So we need to do better. And so the first rule of optimization, of course, when you have a big task and many pieces, is don't do that. Work you don't do is often work that you don't do, and so it doesn't cost you anything. And so if we can eliminate most of the candidates that are going to be far away anyway, we don't need to find out how far away they are, because they're losers. They're far away. And so the trick is to do that sieving away early. And the second rule is when we do have to do it, let's still not do it. Let's find some surrogate for the actual floating point math that we can do fast, like one long word XOR. That's going to be better than a couple dozen floating point operations. Good. And so we can convert a big floating point math operation, mostly, into a single bitwise integer thing using locality-sensitive hashing. I'll explain that in a little bit. And then the third rule is if we have very high dimensional data, like 1,000 dimensional or 100,000 dimensional, we need to first reduce that to a much smaller dimension. And we have guarantees that we can do that with high fidelity for Euclidean distances if we keep at least log of the original number of dimensions, or the log of the average number of dimensions if we have sparse data. And so that's a very exciting result, because that means if we can solve these parts in 10 to 40 dimensions, we can solve it for basically any problem that we have practically. So here's our strategy. First rule, don't do it. Second rule, don't do it. Third rule, make it smaller so we can do it. So now, if you think about it, clustering helps nearest neighbor search, but most clustering algorithms require nearest neighbor search internally. What can you say? We're going to have to break that. And we're going to break that with a couple of heuristic sorts of search. Here's one. Remember we talked about reducing the dimensionality? Well, we can reduce it to one dimension, because one dimension means it's totally ordered, and we have classy data objects like a Java tree set, which search efficiently in one dimension. And the cool thing about linear projections is things that are close together originally project to points that are close together. There's some oopsie factor in the things that are far apart could project to points that are near each other. So we're going to have kind of a false positive thing. The true answers are still going to be close together, but there's going to be other things that are going to drop in close together. And so in each projection that we do, we will find some of the close answers. We will find all of them in some distance, but the number of non-close things we have to weed through will be non-trivial, depending on the data that we're looking at. And so the trick then is to not search quite enough in any given dimension, but project it several times. And if we project it once, the probability of finding the true nearest neighbor drops nice kind of 1 over x sort of thing. But if we're kind of in this mid-range of dimensionality, we still have between 10 and 20% chance of finding the true nearest neighbor in just a few searches, and just a few more than however deep we want to go. And so if we do several of these, the probability we don't find a particular nearest neighbor goes with the product of 1 minus that. And 1 minus 0.2 to a very plausibly small number becomes a very small probability of error. And so we can scale this in terms of number of points and things like that. And so if we just do several of these projection searches that are randomly oriented, so they're independent, we can find a pretty good approximation of our nearest neighbors with only examining a small set of the total points, typically 10 to 40x fewer than we need to do otherwise. Here's the second acceleration method that we're going to use. Each random projection, just like we saw a random projection just a little bit ago, and we used the distance along here to order these things. The second method is only going to use the sign of that dot product. That projection, that distance here is a dot product with the normal on that. And so if we just take plus and minus, bits is 1, the bit is 0. And if we do that repeatedly in independent directions, we get independently distributed bits for random vectors. And the cool thing is that if the vectors are roughly in the same direction, then these bits will tend to be the same because they will be all positive or all negative according to what direction the two vectors that are close together are. And in particular, we can show that the L2 distance, just expand that with binomial theorem, the distance squared of the x and the y, and Mahout caches these, so we don't need to worry about the cost of those, and a dot product in the middle. And the dot product is the magnitude of x and y, which is the square root of that, so we have that cached, and the cosine of theta, the cosine of the angle between them. And the angle between them can be approximated by the 64-bit XOR that I mentioned before, where we have 64 random projections. And if the XOR has lots of bits different, then we're pointing in opposite directions, meaning where it's plus, it's always minus for the second vector, and where it's negative, it's always plus for the second vector, things like that. If the XOR produces nearly no bits, then the cosine will be quite large. And so by just sieving on this cosine value or scaling it according to that previous expression, we can bound away most of the arithmetic we want to do. So we can combine the projection and this, if we like, to get a decent nearest neighbor thing. Here's how much that LSH search works. These are different strategies for picking a cutoff, the different adaptive strategies, using the 75th percentile of the results that we have so far to use as a strategy as one, or using the worst XOR for the things that we've found so far. And we get 25 to 30 speed up in these sorts of cases to get roughly the same accuracy. That's pretty cool. So now we get back down to k-mean search, which is the one that we really wanted to do. So what we're going to do is we're going to do clustering with lots of clusters, little bitty clusters, and then we're going to search the nearest clusters to find the nearest points. And we'll use LSH or projection search in those clusters to search those fast. And if we get a final result that's 50% overlap with the true answer, we're going to win. But we lose if we can't cluster super fast. More on that in a moment. Here's a picture. We've taken that original data that we had before, and we've clustered it with way too many data points according to most people's idea of what a good clustering is. Most people would say there's 4 clusters there. But in fact, what we really want, and when we have lots of data points we can do this, what we really want is something that describes the distribution of unseen data reasonably well. And reasonably well means how many bits does it describe which cluster it is, and the residual squared error for the data point. Those two combined tells us how good the clustering is in describing the distribution itself. And this is pretty good. And so now this is the tessellation, which tells us that this cluster is this region here. And if we want to do, there we go, the nearest neighbor for this point right here, we only need to look in a few nearest neighbor clusters. Now, in higher dimensions, it's not that simple, but it still works reasonably well. So, the speed-ups of 100 to 200x are what we've seen so far, and that gives us, instead of our 6-hour goal, we're at about 12 to 18 hours. Close, not quite there. And in general, the random smooth data that we've been testing on up to this point shows considerably worse results, lower speed-ups and lower overlap, than the actual real data that the bank has, which I don't have access to, but I can simulate clumpy data, which gives those same sorts of speed-ups. So, definitely need fast search, we definitely need that, but here's where the clustering comes in. And this is what makes it all practical, because in this k-means clustering with the LSH underneath it and things like that, we're talking about clustering into 2,000 or more clusters. And if you look at it, the classic algorithm for clustering is something called Lloyd's algorithm. It's now part of CS4 Glory. I mean, everybody knows this practically by heart, just from living around computers for a while. It was developed in the late 50s by a guy called Lloyd, a great coincidence there, but it wasn't even published until the late 80s, because everybody just kind of knew it from the grapevine. So we initialize centroids somehow. There's a variety of ways. Pick them randomly, pick data points randomly, pick averages of several data points. There's a lot of ways. And then for each of many iterations, and this converges quite slowly, so you do wind up with lots of iterations. For each data point, put it in the nearest cluster, and then recompute the cluster centroids. Rinse, lather, repeat, that sort of thing. You get very highly variable quality, but some of the results that you get are pretty good after you restart a couple times, and depending on how you initialize these things. Now the problem is here, it's saying for each data point, find the nearest cluster. That means we have to compare against every nearest cluster. If we want a lot of clusters, that's a lot of comparisons. And each one's got a lot of arithmetic in it, and we have to do many iterations. And that means it's not online or any of the other Knight's properties. So this is a fine algorithm in terms of results, but it's crappy for big data. Just horrible. And here's another one that's more reasonably sized. What they do is they improve k-means by initializing with a clever random picking of data points. And then what they do is they define a distribution on starting points, which are selected from the real data points, such that the probability of any given configuration is proportional to the total distance between them. So they prefer to pick things out there, but if it's way out on the tail, there's fewer data points to pick, and so it robustly picks not quite so far out on the tail. And the cleverness about this initialization is it almost certainly picks data points. If you have well-clusterable data, it will pick data points in the core of the clusters you have, somewhere in the core, kind of near the centroids. And if they're in the core, then if you sample only the points that are considerably closer to the centroid you have than to the nearest other centroid, you'll get points also in the core, and the new average will almost certainly be very close to the true centroid you want. And in the original paper that describes this, they say do one iteration. They prove that one iteration is good enough for a lot of kinds of data that are not very realistic. That's nice. I mean, it's very difficult to prove anything about Lloyd's algorithm. And so this is a very exciting algorithm because it was the first single-passed real guaranteed clustering. The trouble is it still has this very troublesome nearest neighbor operation in it. So we still have, for all the data points in the world, for all the clusters in the world, kind of product. That's not so good. And you also actually still have several iterations, and the initialization is now expensive because you now have to be comparing each data point against all of the already chosen centroids. So we've moved a lot of the computations up into the initialization, and we still have some iterations that are quite expensive. So we're not there yet. So recently, I think 2010 in NIPS, there was an algorithm described that is what I call a surrogate method. That's not what they called it. They didn't name it. So we don't know what this algorithm is. But they start with a very sloppy clustering of the data into many, many more clusters than they finally want. And they want K in the end. And they do this sloppy clustering online into kappa clusters. Kappa is roughly K, their desired number of clusters, times log of the number of data points they've seen so far. And then they use these clusters as weighted data description of the original data, and they do a weighted ball k-means on that surrogate instead of on the original data. And the cool thing here is the sloppy cluster can be shown to be good enough so that the clustering of the sloppy clustering is a very good estimate of the clustering of the original data. And the sloppy clustering is one pass through the data in an online fashion. And the final clustering of the surrogate is an in-memory small data operation, so it's a constant cost roughly. And the results are provably high quality for highly clusterable data. And the sloppy clustering can be done online and fast, faster than the comparisons against all clusters. And yeah, like that. And we can also do that ball k-means pass at any time for a variety of values of k. So without keeping the data around, we could be producing this surrogate as we go, surrogate, surrogate, surrogate. And then at any point, so he can say, give me 3 clusters. And he can say, give me 20. And I can say, give me 50. Without keeping all the data in there, we can do this variable result in an online variable at any time kind of fashion. We just have to do the quick ball k-means in memory of the surrogate. It's a very cool result. So here's the exact way that it's done, or at least the costs. So for Lloyd's algorithm, we have the cost, the number of clusters times the dimension times roughly the log of n, which is the number of iterations guessed. It's probably more than that. And so for k equals 2,000 and n equals 2 to the 8th, we can have things like 50,000 as that order of the size of this, the cost of this thing. The surrogate methods do a fast thing with a kappa of k log n. They do a fast, sloppy search using those approximate methods that I mentioned a while ago for the nearest cluster, which gives a close enough cluster. And so that's order d log kappa, which is order of d, and the d is the same, of log k plus log log n. So instead of k in this order up there, kd log n, we now have log k. And instead of log of n, we now have log log n. And this is a big deal. The difference here is 50,000 versus 17 for a lot of data, 100 million data points. That's a big difference. That's 3,000 times faster, roughly. And like I said, it's a bona fide big deal. I've probably said that 5 times now. The internals then, the way we implemented this is we made new kinds of vectors in Mahout. One is a delegating vector, which takes a vector, just wraps a vector, but allows you to add behavior to a vector. So one of the behaviors is a weighted vector, and it retains a weight. That's no big deal. And you can add another weighted vector to it, and it gets a new add and a new weight. And we have a centroid, which is a lot like that, except adding a new vector to it updates the centroid and keeps an average as you go along. We have searchers, brute force, that's for reference. Projection search, we saw that. K-means search, searches a clustering for the nearest things. And LSH search. And we have the streaming k-means and a ball k-means. I should have written ball k-means, not k-means. We have k-means as well. But the ball k-means and the streaming k-means are the classes that implement the fast clustering. And the interior sloppy clustering algorithm is quite simple. We start off with a threshold, and we make it pretty small. We make it pretty small by sampling 1,000 data points, finding the closest to, and making it smaller than that. Okay? They're small. And we find approximately the nearest centroid so far. If there are none, there is none. And the distance is some infinite value. If the distance is greater than the threshold that we have right now, we have a new centroid. If it's less than that, then with a variable probability, we either add it to that nearest cluster or not. We make a new cluster. And the number of clusters, centroids, is going to grow over time. Very quickly when the threshold is tiny, because every new point will be a new centroid. And once they get larger than about something like 10 times the log of the data points we've seen so far. So if we've seen 1,000, then log of n is like 10. So once we have more than 100 clusters out of 1,000 we've seen so far, or 100 clusters out of 100, then we recursively cluster the centroids with a larger threshold and make the threshold bigger. If this recursive clustering drops the number of centroids dramatically, then we leave the threshold where it is. If it doesn't make it much smaller, we increase the threshold multiplicatively. So eventually the threshold gets big enough that we're adding to existing clusters a lot of the time. And we're smashing it down every time we recursively cluster it. So we're going to look at every data point exactly once. The initial centroids are going to wander all over. They're not going to describe the initial data points at the end. But we do have guarantees about how this final set of centroids, which is going to be much larger than the number of centroids that we really want. We know that we can prove, I can't prove because I haven't read the paper carefully enough, that this centroids will be a usable surrogate for ball k-means clustering with a guarantee on the quality later. And so we can do those on the fly. Anytime we want is cluster those surrogates. And we also know that the number of surrogates, the size of the surrogates, is relatively small. It's k times log n. And so 1,000, 2,000 times the log. Suppose we have 100 million, the log of 100 million is like 26. So we want like 26 times 1,000, 2,000, 50,000 centroids. It's tiny, it's megabytes of memory. It's just not very big anymore. And it only grows logarithmically, so it's never going to hit a megabyte. It's just never going to happen. And so the in-memory part is quite small, and the cost of clustering that is also quite small. Here's the parallel speed up of that sloppy clustering thing. And the reason that it speeds up this way is if we sloppy cluster 2 fractions of the data, we get sloppy descriptions of each of those, and the union of those is just fine. Even if those 2 things got exactly the same centroids, that's still a fine description of the data. And if they're off a little bit, that's okay too. All we wanted is some surrogate of the data density, the probability density distribution of that data. And so we can trivially make this parallel, and then at the end take the union of all of those in-memory representations. We can fit a lot of those in memory, hundreds or thousands of them, and we do the clustering on those. Or we even do just that recursive clustering to make it as the size we want. Shazam. And so here on a single machine with 16 cores, we see nearly perfect scaling out to around 12 cores, and then things degrade a bit. But you know, there's a couple of threads that Java keeps back for garbage collection, concurrent garbage collection. That's probably what we're running into here. We probably only add about 12 threads to work with. And so there's very, very little cooperation or interaction between these threads. We get perfect scaling. And the result here is a good surrogate for the data we've seen. And the speed, as you can see here, this is at 10 dimensions of randomly distributed data, is 20 microseconds per data point, 1 pass. 1 million data points in 20 seconds, 100 million in 20 minutes. That sort of thing, 30 minutes. And we can do this again on the MapReduce level. So this will scale horizontally. the same way it scales horizontally with threads using MapReduce. So we could do our 100 million data points clustered on 100 machines in about 20 seconds. Now, the overheads are going to be substantial, so it might be several minutes. But several minutes to cluster 100 million data points, it's just damn fast. Sorry, check. Yes, parallel speed up. I wouldn't want to pass that up. Any animation I can put in a slide, I'm so proud of it. So MapReduce implementation, as I said, is trivial. Just do the surrogate on each piece, and the surrogate on each piece might be recursively subdivided and then the union. The reducer is just the concatenation of those, and maybe the recursive clustering just to make it small. What?
Reducer just with one more pass.
Yeah, one more recursive pass. So it's going to be tiny, just like that. And you might even have a combiner if you want. These are all simple, but it's so small compared to the input data, you don't need the combiner because the amount of data moving around is tiny. And so the threaded version shows pretty much exactly linear speed up, and the MapReduce version should do almost exactly the same. Not entirely guaranteed. There's always surprises when you try to move data around. But the splits should be, there's no interactions, so it should be good. We have, so it wasn't from 2010, it was from 2011. Schindler, Wong, and Myerson is the key paper on this, and they provide references back into the Vol K-means paper and previous work that was considerably more complex than this. I've got a detailed workup of the algorithm that I've done on the GitHub repo where I've published all this code. I varied their algorithm somewhat because it seemed impractical and somewhat theoretical in spots, and you could tune it here and there a little bit. And need results here is a kind of an important step there, but I'll be getting that in shortly. So we can make nearest neighbor algorithms blazingly fast, like thousands of times faster than they are in a brute force case, if we can do fast clustering, and we now have blazing fast clustering, commonly known as super fast clustering. And it's online, so it's just all those wonderful things that we wanted at the beginning. So we're hiring. We need people to do cool things like this and write them up and give presentations and help customers do this. This was part of a workshop where this bank sent 12 developers for, 6 developers for 2 weeks. In the first workshop to our facilities, we did an intensive 2-week hackathon. They got up to speed. We got new code. The deal was that it was open source, so we could maintain security. I love that argument. The fact is, I couldn't touch their code, and they couldn't use our code because that would imply all kinds of ownership issues, because there was a third party for contracting it, and I couldn't touch their data, so we used random data and open source code. Everybody was happy and maintained all of the proprietary interests by being completely open. I thought that was fun. You can send me email. I'm also ted.dunning@gmail. I'm tdunning@Apache. You can send me email any way you like. There's tweeting to be done. There's some hashtag for this tonight. I don't know what it is. And there's a nice short landing page URL there for the slides, for anything else you need, links to me, the abstract, and any other information people need. There's a GitHub repo on there, my account, tdunning/KNN. And you can grab all the code and write-ups of how this works. There it is. Any questions?
What's that again, the GitHub?
GitHub tdunning, just like here, /KNN for K nearest neighbor.
Okay, K nearest
Yeah.
neighbor.
And I'd love to have pull requests or anything like that. I'm moving this into Mahout slowly. Sadly, I found some bugs in the vector code. When I fixed those, it broke the build, and so it's going to be slow. But it's usable as it stands in isolation, and it builds with Maven, so it's easy to build. So, like I said, other questions? Yeah.
Yeah.
We have a question from an outlier.
Oh, right. You've heard of self-organizing maps, right?
Yeah.
So how does the last algorithm differ from self-organizing maps?
Self-organizing maps are kind of a weird little animal. The idea is that you move map centroids around according to the values that are nearby, and so on. And they were developed by Cohonen in the 80s when everybody was kind of just in the wild, wild west of clustering and learning algorithms. They have some interesting properties, but I think that the interesting properties that I've seen are no more interesting than just cluster centroid distance features, at least for learning. They have additional properties that are nice in terms of visualization. And various people have put interesting landscape sort of metaphors on top of SOM projections of high-dimensional data. SOM algorithms tend to be very slow to converge.
Okay.
Lots and lots of cost to doing them.
I thought they were fast, but I'm probably mistaken.
They're slow gradient descent sort of algorithms, and so they're not on large data. They're not. Now, one exciting thing is you very likely could train SOMs using surrogate techniques like this, and so you could have effectively an online super fast SOM training where you would train it on hundreds of millions of things in the blink of an eye. After you've passed through those 100 million things. And you could pass through them in parallel because the surrogate is all you care about. And obviously the MapReduce thing could be replaced by something like a storm topology because it's all online. And the thing that's combining those surrogates could sample everybody and just do it quickly. And they are L2 based as well. The metric is typically Euclidean. That would match very nicely here as well. Yeah.
Yeah, and you were mentioning in the process as you're instantiating the clusters in online mode that there's some probability of adding a new cluster at each additional point.
That's kind of a weird idea.
A lot of this is reminding me of Chinese restaurant processes you're going through it. Is there some clever way of choosing whether or not you add a point as a new to see the new centroid, or is it really just best to do a probability of whether you want to add a new one?
This is the probability.
Yeah, exactly.
And in fact, the algorithm has stated when D is less than threshold, it picks a uniform 0,1 deviate and compares it to D divided by the threshold.
Could you use
and so it's uniform even. It's really simple. But in fact, just like the initialization of vol k-means, this non-determinism is actually critical to probabilistic convergence.
Okay, so that sort of gets at my point. I was wondering if it would make some sense to measure distances at that point to decide whether or not to use it to seed it in cluster.
Well, you are measuring the distance. You're measuring the distance D to the nearest cluster. And you're comparing it to your current threshold. And you take a uniform and compare it to D over threshold. And if the uniform is less than D over threshold, it's added to that closest cluster. Otherwise, it's a new cluster.
I see. So the context of the rest of the clusters in the set of clusters you're currently using are irrelevant.
Well, they are implicitly present in the distance to the nearest one, because you know that they are no closer than that, because this is the nearest one.
Yeah. Okay. And then my second question was, can you extend this to doing multiple cluster assignment per point?
I think that is actually the essence of the non-deterministic assignment here. I mean, but you could, yeah, you could say something like where you see added to the nearest centroid, we could have non-deterministically added it to any of the nearest centroids according to their distances. That doesn't seem to help the convergence of this sloppy phase. Now, in the vol k-means, this here does do that. And it's a nice sequential implementation, but it samples the initial points according to probability that is proportional to the sum, or the total distance between all of those initial points. And so it is providing those multifactorial sort of comparisons in a very interesting way. So the sum of all of the square distances between all of the initial points is the probability, is proportional to the probability that the configuration is selected here. And they do that, they have a clever sequential selection algorithm to do that. And that's a lot like what you're talking about, I think, because the probability that any given point is going to become a seed centroid is proportional to the distance it is from other points.
Right, and so this is done in the initialization phase, so if you wanted to do a multi-membership for a data point, you would do something similar to that.
Well, these algorithms are stochastic as opposed to truly multi-member. And so what they do is, instead of saying multi-member, they say this incarnation of this instantiation of the random sampling gives us this hard assignment. But in fact, what we're doing when we do that sampling is we're reasoning over all possible assignments by a sampling algorithm. And it turns out that we can do that reasoning in one sample because of the guarantees. If we had weaker guarantees, then we might have to do this assignment many times. And indeed, you have to do that in k-means. That's how you get the probabilistic, non-deterministic sort of multi-membership in k-means, is you run it many times. Here, the probabilistic guarantees are far sharper, and so a single sample almost always suffices to get you the results you need. And the results we need here are to sharply separate sigma-separable clusters. Sure. And, you know, there's always an argument about these fuzzy sort of things. The fuzzy assignments very often can be viewed as mixture model derivation. So you, instead of cluster being, or the clustering being, it's this one or that one or that one, it's a mixture model. It might have been this one, it might have been that one, it might have been this one. And that's a nice way to describe data. But if it is sigma separable, then the tails are weak on top of each other, and so hard sampling is okay. In other cases, we want to do something like Gibbs sampling of a less discriminating sort of mixture model. And maybe these things are good there. But if we have a good description of the underlying distribution, we can do those as the follow-on step rather than the sloppy step. Yeah.
Yeah, glad to know that your company is hiring. What kind of people you are looking for? What kind of skill set, you know? And do you hire consultant?
No, we're looking for full-time people. So the people, I mean, the first qualification is really smart. That's a critical thing. Really flexible in terms of what you can work on. Experience in big systems is very helpful. That doesn't necessarily mean Hadoop. It might mean very large storage systems or very large other kinds of high-performance compute systems. That's helpful, but the first qualifications are very smart, and very smart in a practical sense. So a history of creating practical large-scale systems is the best indicator of really smart. A second indicator is really well able to explain ideas. I often give interviews with one question: draw me a picture of the last thing you built. And then I start asking why. And if you don't know why, we're done. Usually. I want people to think about these things, come up with reasons, right or wrong, but they know what they know, and they know what they don't know, and they know why they did things. A mindful approach to designing is what I look for. So it's very difficult to say, but you kind of know it when you see it. So that sort of thing.
The very smart qualifier doesn't apply to the sales department, though. So, in In the sales department, you just have to be as smart or smarter than me, and that's kind of a lower bar.
Yeah, but you also have to be as productive or more than he is, and that's a much higher bar.
Yeah, agreed.
Any other questions? These guys don't look like sales guys. They look much more like the other kind of.
Figured I'd be thorough.
Okay. Well, thanks. Thanks for coming. This is fun stuff.